specifications for now. So Slalom will develop machine learning for robotics into performance guarantees for learning-based
Welcome, everybody. Thank you so much for the invitation and for organizing this amazing conference. So my motivation to look into machine learning was because I work with real robots, and robots are complicated. So let me give you some examples. So this is a swarm of robots we have in our lab. We want to achieve really high performance, high tracking performance, and obviously there are complicated aerodynamic effects. We also fly these vehicles outdoors based on vision at speeds up to 55 kilometers per hour. And during our tests, we have winds up to 28 kilometers per hour. And so we want to fly these vehicles reliably, given that they are outdoors and quite heavy and dangerous. Also drive outdoors in varied off-road terrain. And safety here means that we don't get off the path while trying to optimize the performance and the speed of this robot. And finally, we are part of a self-driving car competition, and we had to test in winter conditions in Toronto. And our algorithms had to be robust enough to drive at the competition in the desert in Arizona, and we had exactly 10 minutes to tune any of these algorithms. So what all these examples have in common is that these robots must achieve high performance in a wide range of different conditions. And these conditions can be environment conditions, but in the future, different conditions may mean working with different people and in collaboration with people. And this generally challenges traditional robot algorithm design, which looks usually like this. It's kind of a closed loop, obviously. We have sensors, then some state estimation, mapping, a planning component, and eventually motion control. And all of this is hand engineered. It's manually programmed and based on a priori knowledge, for example, first principles models of the robot. So this approach is limited by our understanding of the system and its environment. And to enable the applications I showed you in the initial videos, where we have a wide range of different conditions, we really have to enable robots to learn and adapt to achieve high performance in those conditions. So learning and adaptation in this case can mean many, many different things. You can put a learning component in every module, in your vision module, in your planning module, in your control module. You could do one big neural network end-to-end from pixels to volts. So I think one really big and interesting question is, what is the right learning architecture and approach for closed-loop systems? And I don't think it's really answered yet. So the approach that we have been taking over the past few years is combining machine learning and control theory, which is the theme of this conference, which is great. And in my opinion, control theory is really the science of feedback. So it's the only science that looks at these closed-loop systems and analyzes and defines stability, performance, and robustness. And then on the other hand, we have machine learning, which is the science of data and inference. And both together are a powerful combination to tackle some of these problems. The particular focus of our group has been, because we work with real robots in the real world, on data efficiency, because we operate these robots and every data point costs money and time. On online adaptation, because we don't assume we have simulation environments that really reflect the real world. And safety guarantees for these closed-loop systems, because you saw some of the robots that we work with are quite serious, and it would be traumatic to kind of destroy them. So what I thought I am going to do in this talk is kind of just highlight 3 themes of the research that I found, where I can show you how control theory and machine learning can nicely work together. And so the first one is architecture and hierarchy. So control theory has helped us a lot in appropriately placing the learning in the overall system architecture. So control theory and generally system dynamics allows us to understand the system, even if the system is complicated and we may not be able to identify all the components of the system. It gives us an understanding, and especially an understanding of systematic versus random effects. Where systematic effects are things that a learner can nicely learn from data, versus random effects where the best thing you can do is really doing fast feedback. And then, as an example here, for flying vehicles, you have these kind of nested control loops, starting with the lowest control loop, which is motor control. So the motor controller just makes sure that the motor spins at the turn rate that you want it to spin. And then at the highest level, if you kind of close all these nested loops, you have position control. And in the middle, there's a controller that makes sure that a turn rate around a body axis is achieved. And so by kind of closing the right number of loops to make this, to account for the random effects with feedback, we have kind of a repeatable input-output pattern that is then easily learnable in machine learning. And I think that's kind of a nice way to where both control theory and machine learning can complement each other. So one very early example that we did is a robot learns a single task through a repetition. And so there we close the feedback loop such that the system is stable. And then we learn the reference signal, the input signal, such that the output does what we want it to do. And so the very basic idea is that you do run the experiment. You see how much the actual output deviates from the desired output, which is delta y. Then you use a rough first principle model that relates this output error to a change in parameters. And so you change the parameters of your reference signal iteratively in the right direction to eventually get good performance. And so we did this on flying vehicles and did this S-shaped desired trajectory. And if we learn the desired turn rates, as an example, directly, we can learn that, and we can, our learning converges. But the result is that after the reference input converges, we apply this reference inputs repeatedly, you see the red lines, and they are not a nice S shape. And the reason is because we didn't close enough lower level loops such that there's still too much randomness in the system that the ultimate performance that we can achieve with our learning controller is not good. But if we instead do this on desired positions, so we learn desired positions, and no feed forward, because that was kind of the configuration that provided us the best and the most repeatable behavior, then the learning can actually converge, and the converged reference position input leads to a repeatable behavior in the output, and we nicely follow this S-shaped trajectory. So we use that for slalom racing, and in this case, if you don't use learning and there's quite a lot of unmodeled aerodynamic effects, it really doesn't work as you would hope. And so we use exactly the technique I described. And because we close all these underlying controllers, it converges very quickly. And the other reason for the quick convergence is that we use our prior model information as a gradient in the learning. And so after 3 iterations, we can actually do this, and we can learn arbitrary configurations. But this was a task-dependent learning, so every configuration needed to be relearned. So we thought about an idea that we can learn a model instead, and learn once this model and use it for any arbitrary trajectory. And the setup is quite simple. We just put this pre-block there. We use a deep neural network in this case, but you could use another nonlinear regression technique. And basically, this neural network needs to approximate the inverse of the dashed green box. And we showed, and again from control theory, we can kind of quickly get insights. So if this, even if we know nothing about this dashed green box, if it's kind of a generic nonlinear system, if we do the inverse, we would know that what would need to sit in this blue box is this function f, which is dependent on the state, and the desired output are steps in the future, and r is the relative degree of the system. So the control theory, even if we know nothing about the system, can tell us what roughly needs to sit in this black box, in this blue box, and help us to choose the right input features. And so those input features are relatively easy to get, and even if you don't know R of your underlying system, you can do a quick test, like a step response experiment, to get this value, and go from there and learn much more efficiently than thinking you need any more input features. The good thing is we learn this box from a number of trajectories, and then we keep it fixed, and we can be better in tracking any new trajectory. And so here's an experiment. The idea was that you can draw something on the tablet and that the controller follows. And this is the performance of our standard controller. It's not great. There are many non-idealities in the system. And then we add this learning block, and the tracking of this red dashed line gets much better. So usually we have a performance improvement of over 40%. And so we did a lot of kind of tests in the lab where people would draw different trajectories. And we know from control theory that a standard controller would not be able to perfectly track any of these trajectories, even if we would know the model perfectly. And so you see that the performance is improved even for complicated drawings. So if we look at this idea of architecture and hierarchy, what it really helped us is that control theory told us where to put the learning in the closed loop, and this helped with data efficiency and also with stability and performance guarantees, because as you saw, the learning was always outside of the inner loop, so we could make the inner loop stable, and as long as the output of the learning system is bounded, we have at least bounded input, bounded output stability. So I think there's lots to explore there. These were just two examples of how you could play with where to place the learning in the overall architecture. Another interesting area we have been working on is how can we achieve safe learning? If we drive these robots outside, we want to guarantee with high probability that they don't crash. And so control theory has really nice methods to guarantee stability and performance for uncertain systems. That's robust control theory. Usually these uncertainties are fixed a priori. And then, they use techniques such as Lyapunov theory to prove stability. On the other hand, machine learning, if we make very weak assumptions about the unknown effects, such as continuity assumptions, there are probabilistic learning models, such as Gaussian processes, that provide us high probability bounds for a function. And those high probability bounds shrink as we gather more data. So this may look like this. So initially, we have no idea. It could be anywhere in this light blue envelope. But then as we gather more data, we get more certain in certain areas, and we can adapt our controller up. And so one of the first approaches that we did was that we model our system like this. We have an a priori model, which can come again from first principles, a kinematics or dynamics model, and then a model error that we are learning. And we used a probabilistic learning model in order to specify those uncertainty bounds. And initially, we need to assume that our true function lies between the initial assumptions of the uncertainty bounds, so you can make them quite large. But then as you gather data from the system, you learn more about this model error, and you shrink those uncertainty bounds. And with some formal assumptions, you can guarantee that those uncertainty bounds that you get from your probabilistic model are actually true high probability bounds for your system. And then we use robust control. And one early approach that we did was we combined this probabilistic model with robust constrained nonlinear model predictive control for doing off-road path following, where we want to increase the speed of the robot as it learns more about the world. And so how that works is you can look at this picture. So at a given moment, the robot sits here. And with model predictive control, it uses its model to predict into the future. So for a fixed input sequence, the robot may end up anywhere in this envelope. And the reason why it's ending up anywhere in this envelope is because we have this stochastic model, like this Gaussian process, which doesn't tell us exactly what the robot does, right? And so before learning, we have a high uncertainty, and what it does is that it reduces the speed, meaning that over a fixed prediction horizon, we don't get as far, but it makes sure that we stay within the path bounds with high probability based on our probabilistic model. And then after learning, the probabilistic model is more certain, and we can try faster without getting off the path. And so we did a lot of off-road testing. So here's just one example. On the left, you see the robot driving the first time. And on the right, the robot driving the same path the third time. And so it drives significantly faster. You see the uncertainty envelope is smaller. And we drove with this robot, with this method, faster than we have ever done without being too worried that something happens. And so it finishes this particular segment of the path faster than it did in the first round. We also tested this on 4 different robots without really retuning the algorithm. So one robot was from the Canadian Space Agency, one from Defense R&D Canada, and one smaller robot in our lab. So it really showed that it's basically applicable on various robots. We also have really interesting results, more recent results on safe model-based reinforcement learning. I assume that this is in collaboration with Andreas Krause, and I assume he will tell more about that. But the idea is that reinforcement learning usually doesn't have a notion of not trying out actions that very likely lead to disaster in some form. So this is kind of crazy. First, you try things out that in a real system, you try things out that are dangerous. But even if it's in simulation, you would think that this is not very efficient. You try things out that you know possibly a priori that will not lead to success. So why should you even try it out? And then we also used Gaussian processes in a more model-free approach to do safe automatic controller tuning. And we applied this to tune an adaptive controller, which was really interesting because there's no really optimal tuning strategies for adaptive controllers. So in summary, when we kind of combine these 2 techniques for safe learning, we could achieve safe exploration under some assumptions, of course, data efficiency, and certain performance guarantees. Again, whenever you need to do the proofs, which I omitted here, you make some very weak assumptions, but our goal is always to make very weak assumptions about the things that we don't know. So here, in this case, about the unmodeled model error, or unknown model error. So finally, the last idea is something that we are very actively working on, and it combines fast adaptation with long-term learning. And so from control theory, we know that fast feedback is a really effective way to control a system, even especially under disturbances. And so our idea here is, can we combine fast adaptive feedback control to force the robot behavior in a particular way, and then do high-level learning? And the idea is that this is an image of our off-road robot traveling the same path over 4 months. And so it experiences, in Canada, we have freezing rain, we have a lot of snow, then at some point it's really wet, and then eventually maybe there's spring in May. And so these conditions are really hard to predict, and if the robot goes out and has never seen this condition, the best thing you can do is really, really fast feedback and really adapting very quickly. But then on the other hand, you think that you could learn something from this winter for next winter, so you could rediscover a condition that you may have seen before. And so on the control side, we looked at L1 adaptive control because it allows or provides some formal bounds of the difference between the actual and the desired behavior. And then on the higher level, we use techniques that you saw before, similar to the Slalom Learning or the off-road robot. And so adaptive control, especially this L1 adaptive control, it provides you a bound between the output of what a reference model would do, a reference model that you specify, and the actual system under the L1 adaptive controller. And this difference is bounded by a function that's proportional to 1 over gamma, where gamma is an adaptation gain that you can choose very large. So you can make this difference small. And so what that means is if you put this adaptive controller at the lowest level, the dashed box performs very closely to a reference model that you specify, which could be some linear or second-order system. And then you can put on top something that further improves the tracking performance or does some other higher level learning. And so if we do that, then the goal is that, in our case, a simple goal is that the desired trajectory matches the actual trajectory. And so as a first test, we tested it on a flying vehicle. Here you see the flying vehicle doing a certain task multiple times. And on the y-axis, you see the average performance. And so as it does the task multiple times, it gets better, similar to the Slalom Learning. But we do it for different underlying controllers, a PD controller, PID controller, and this L1 adaptive controller. And then we introduce a wind disturbance. And that's what we see. So we introduce the wind disturbance. And basically for PD and PID, this higher level learner needs to relearn. But with this adaptive controller, the adaptive controller takes care of the wind disturbance, and the high-level policy can be reused. So the adaptive controller really handles the disturbance. And then we were wondering, can we even use that to try it on a different system, like transfer from one robot to another robot? And so we did some first experiments. We are in the process of doing and analyzing this more, where we transfer this knowledge to a similar but different robot, different in weight, different in the inertia values. And here we try to do the same task with both of them again. And these are the results. So again, really the high-level learned policy can be readily used again because this L1 adaptive controller makes those two systems basically look the same on the higher level. So that was quite promising. And then we recently extended this work to learn with one robot a task A and then use that knowledge to do task B with another robot. Again, relying on this underlying controller, and this actually works really well and is very simple multitask, multi-robot transfer with very, very little data. And another very recent result is where we really store for this off-road robot any data point that we get and do, on the one hand, fast adaptation with Bayesian linear regression and long-term learning to improve our predictions of those systems. So overall, by combining this very fast underlying feedback with high-level learning, we could get safety through fast adaptation, and we can long-term optimize our performance. And we work both on more formal proofs, especially for the last work I showed you, the what am I doing? Anyway, we work on formal proofs for some of these and have proofs for simplified scenarios for other techniques. So you can look at the papers for more details. So in summary, we in control theory, we should be concerned about learning for physical closed-loop systems. And I think the concepts from control theory are really relevant and interesting to analyze for learning systems, and concepts like stability, convergence, robustness, performance guarantees, all these things have been defined in control theory and are not necessarily known to people in other communities. And then in our case, we showed for some very specific cases that we can be very data efficient, achieve online adaptation and safety guarantees during learning by combining machine learning and control theory concepts. But I think there's many open questions, and some that I find interesting are how can groups of robots learn? Like, when can knowledge from one robot be transferred to another? What is a measure of similarity between robots? How can we extend these techniques to interaction tasks, where robots actually interact with the environment? I think also an interesting question is, how can we combine reinforcement learning and imitation learning? So can a robot ask for help when it's needed and a human could provide input? Then we got stuck with stability and maybe trajectory tracking, but what about much more complex task specifications? Again, long-term and short-term learning and how to trade that off, and how to eventually couple perception and control, because really what we see in robotics is that almost every single module in this closed-loop system, from perception to control, has learning components incorporated at this point, especially in application areas like self-driving cars. So how do we analyze that and properly design that? And so there are many more questions. I think it's an interesting area, but people have made progress in small ways, but I think there are many open questions. So if you are not convinced and think this is not true, read the Science Robotics article where they highlight 10 grand challenges in robotics, and one of them is aspects of artificial intelligence, and they highlight things like limited data, learning on the fly, enabling robots to seek for help, and generally doing complex tasks. With that, I'd like to thank my team collaborators and all the funding sources, and I'm happy to discuss more of our work later, and if you are interested in joining my crew, please let me know.
Thank you very much, Angela, for the very nice presentation. Everybody's keeping so well in time, so we have enough time for questions. Yes, we start in the back. Yeah.
Hi. So I think the idea of having the adaptive control in the inner loop is a really good idea. Just one sort of technical note about that L1 controller. That bound of 1 over gamma isn't sort of unique to the L1. It's actually, there's a fundamental assumption in L1 that they have perfect matching, and that bound actually isn't uniform. So that's just a feature of the assumption of L1.
Yeah.
So you should just sort of caution you that, yeah. So in the case of output feedback, actually in the papers from that group, they initialized the reference model about state data, which they could never know. So that's just a generic feature that falls from the Lyapunov function and sort of the sum of squares error. So it's just a general feature, just so everyone knows. It's not unique to L1.
Yeah, I totally agree. And we are currently working through some proofs and had to redo a couple of them from the papers. Yeah.
Excellent. More questions? Yes, Sebastian.
Okay, yeah. So I have a question about the trajectory tracking, which looks very impressive. So do you retrain the neural network for every new trajectory? And if yes, is there some hope that you could, if you've seen enough trajectories for these quadrilaters, basically have a general neural network that you could use for all sorts of trajectories?
Are you talking about the hand drawing?
Exactly,
Okay.
yes.
Yeah, it's a single neural network, and it is trained on periodic motions only. The results I showed in the video is trained on various periodic motions with various frequencies, but not even on hand-drawn trajectories. And that's enough. And then we can show that actually if this inverse would be unstable, the ideal inverse would be unstable by the right choice of input features, we approximate we learn the stable approximation, and that is similar in the simplified case to some of the results that have been out there long before.
Okay, and do you have an idea of when you have enough data?
No, that's a very good question, and actually one of my PhD students looks at that. Yeah. No.
There was one question here.
So thank you for your talk. So I remember when you talk about using data and gradually reduce uncertainty in your model. So you mentioned that you were using Gaussian process as your model, right? So my question here is, it is well known that Gaussian process models may not scale well, and so the question is, what if you just have a lot of data? Can you still use your method to kind of benefit from the data and reduce uncertainty?
Yeah, very good question. Yeah, so Gaussian processes don't scale well with a lot of data, which is unfortunate. They have this nice property that they give us these uncertainty bounds that are actually meaningful compared to other techniques. When we went now for long-term experiments, we went back and used linear Bayesian regression, a kind of local linear models, because that's enough. We just basically need to predict well enough over the upcoming prediction horizon if we use it in the context of model predictive control, and then we can use all the data. But yeah, I think it's a nice tool to get an intuition what works and do proofs, but then in practice you have to think about your application. Yeah, I agree.
Great, so before we thank Angela again, I just wanted to announce we now have a half an hour break to recharge over coffee and continue our discussions. And with that, let's thank Angela and all the speakers of this first part.